In our previous lecture, we were starting to discuss about linear classification. In other words, the use of linear models to do classification problems rather than just regression problems, right? So linear methods can be used for classification as well. In these cases, the decision boundaries are linear. In other words, a line separates different categories, okay? And despite their simplicity, these methods are actually quite effective across a large spectrum of data sets, even compared to other more complex machine learning models, okay? Now, the first part of the lecture, I wanted to introduce to you the metal insulator data set, all right? So in this data set, we basically have 2,000 binary compounds. Binary compounds are basically materials that comprises of two elements only, okay? So in other words, they have the formula AXBY, right? So they just comprise of two elements, A and B. For the metal insulator data set, we are going to define two classes. The class 0 is basically the metals. In other words, those with band gap close to 0. And the class 1 are insulators, which are things with a significant band gap. Now, using PyMatGen, we can generate some simple features. And for the purposes of classification and for ease of visualization, we are going to develop a model that is only based on two features only. One is the mean of the electronegativity between the elements of the elements A and B. And the second feature will be the absolute difference in electronegativity between A and B, all right? Now, if you plot the data across these two features, this is basically what you get. You will notice that quite clearly there is a separation, right? You see that most of the orange dots, which are basically your insulators, lie somewhere on the top right corner of your plot, and the metals actually lie on the bottom left of your plot. And this is quite intuitive when you think of the periodic table, right? Metals generally have low electronegativity, and if you have a low average electronegativity and a low difference in electronegativity, that usually means that your binary compound is one that is between two metals, in other words, an alloy, and those tend to be metals as well. While if you have very, very large differences in electronegativity, you would typically mean that you are ionic compound with which tends to be insulators. Okay. Now, I showed you the code, and I show you how you can go about constructing these features. I didn't have that much time in the previous lecture to go through this in detail. Today, I want to actually spend a bit more time going through the data set with you and how to use each of the things that I show here. Okay, so let me switch over to our Google Colab. So this is the Jupyter notebook for lecture number 4. So the first thing that you need to do, as I mentioned before, is that for this particular problem, you do need to generate features using PyMatGen. So you will need to install PyMatGen in your Google Colab before you proceed, right? Now, so using the first statement, you have to uncomment it, and you do pip install PyMatGen. You give it a while, it will start installing. Let's just give it like 1 minute or so. Okay, so after a short while, you have installed PyMatGen. Now, one thing you would need to do before you go any further is to actually restart the runtime. Okay, so the reason why you sometimes will see an error with the NumPy version or something is because PyMatGen actually requires a different version of NumPy from the one that comes pre-installed and loaded with Google Colab. Okay, so you restart the runtime. Okay, and after you do that, you just rerun everything, and it should work. Okay, so here is the first cell, and you see that I managed to import everything. So from PyMatGen, we are importing the element and composition object definitions, while the rest are basically the typical things that you see from your for this course, basically NumPy, Seaborn, and Matplotlib. I usually set some default parameters for my graphs because they look a bit nicer. And then what I'm going to do is that I'm going to take the data set directly from the GitHub repository, okay, and that's the binary bandgap data. So I just need to give it the URL of the data, and I use the pandas read CSV method to read in the comma separated value file. And this command called head just shows you the first few rows of that comma separated value file that I just read. Okay, now this is the first few rows of my data frame, and you can see that basically I have the formula in one column. Okay, and the formula is something like AGAU3. The bandgap is 0, and then so on and so forth for different elements. Okay, now you can actually also see that when I put my cursor across this binaries variable that I just loaded, they actually give you some information about the data frame. There's 896 values and 2 columns. Okay, so this tells you that there are actually 896 data points in the data frame itself, and the 2 columns are, of course, these 2 columns over here. Now, one of the things that you need to be able to do is to use the PyMatGen composition object to basically generate data. Okay, so let me first show you what the PyMatGen composition object does. Okay, so I'm going to insert a code cell here. So let's take the formula AGAU3, right? So what happens when I pass something like AGAU3 into the PyMatGen composition class? Basically, what happens is that the PyMatGen will pass this formula and construct a composition object, and the composition object essentially is like a Python dictionary. It is basically a mapping between element and the amount of the element within that composition. So in this case, this composition contains 1 silver and 3 gold. Okay, so that's the composition. Okay, and the PyMatGen composition object has quite a number of features. Okay, so for instance, we can ask for the weight of the molecular weight of this composition, and for the PyMatGen will automatically calculate things like what the weight of this formula is. In this case, the atomic weight, the molecular weight is 698 atomic units. Okay. Now, so to make things a little bit easier for us, what we are going to do is that we are going to construct an entirely new column called composition, and that column will basically contain the composition objects for every single formula that we have here. So this is basically what is called list comprehension in Python. We are iterating through everything in the binaries, the formula column, and we are creating composition objects for each of those formulas, and we are putting that in a new column called composition. And if you look at the first few rows of the data frame now, basically this is what it looks like, right? You still have your formula, you still have your bandgap, and you also have this composition object. Okay. Now, a composition is also a dictionary. So, for instance, if I look at the composition and I ask for what's the amount of silver, you see that it gives me 1.0. If I ask it for the amount of gold, it gives me 3, right? Now, you can also iterate through all the different elements in the composition. So, for instance, this basically just iterates through every single key in the composition itself. In other words, every single element in there. All right, so you see that I get silver and gold as well, right? Now, once I actually get the element, for the element, you need to remember that, for instance, there's this variable called x, okay? X just is standing for chi, which is the symbol for the electronegativity of an element, okay? So I'm going to go to x, okay? And you can see that, well, this shows you that basically the electronegativity of gold is 2.54, okay? Now, so in order for us to create our features, we need to first create a column of the electronegativities, and then we need to calculate what's the mean of the electronegativity as well as the difference in electronegativity, okay? So this is exactly what is done here. First of all, for each of the composition, I am creating essentially a list of the electronegativity of the elements within that composition, okay? So this is what this row does. And then for each of the set of electronegativities, I'm going to calculate the mean. I'm also calculating the difference in electronegativity. So to calculate the difference in electronegativity, I just need to take the maximum of the electronegativity values minus the minimum of the electronegativity values, okay? And finally, I also need to create a column for the class. In other words, what's the classification or category, right? So here I basically create this short method, which basically says that if the band gap is less than 1 times 10 to the power minus 5, I'm going to treat it as a metal. If it is anything else, I'm going to treat it as an insulator. In other words, I give it a label of 1. Okay? Now, once you do that, we can go back to the first few rows again. And this basically shows you the new columns that you have created. You have one new column called mean underscore x, which is the mean of the electronegativity. You have one column called diff x, which is the difference in electronegativity. And you have one more column called class, which is the classification, either 0 for metal or 1 for insulator. Okay? So that is basically we are actually, after having done that, we are actually going to ignore all the first 3 columns that we have started with. Those are actually just for processing the data. The only thing that we care about is actually these last 3 columns over here. So these 2 are the features, and this last thing, this is the classification that we are trying to predict. Okay? All right. Now, did I not run that? Oh, I forgot to run this part. Okay. Okay. And we can plot our data set. This is the reason why we use 2 features. 2 features are actually very easy to plot. You basically have one feature on the x-axis, the other feature on your y-axis, and you can plot the classification as the color of the marker. And you can do this using Seaborn. In Seaborn, there is something called a scatter plot. And for the scatter plot, I'm going to choose x-axis is the mean of the electronegativity. The y-axis is the difference in electronegativity. And the hue, which is the color of the marker, is the classification. Okay? And the data comes from this binaries data frame. And once you do that, you basically get this plot that you see in your lecture notes. Okay? Now, as a general practice, before you actually start doing any machine learning models or any training, that sort of thing, it is always a good practice to first plot out the data, right? Just plot the data, visualize it a little bit, see whether you see any clear trends or any correlations between your data sets, your features, and your between your features themselves and between the features and the target, as well as the and between the target and the features. Okay, it is always important because sometimes you can actually see certain problems with the data set just directly from a plot. Okay, and you can also see whether is it a futile task to predict this or not, right? So in this case, it's quite clear that there probably is some good classification line, right? You probably, if you draw a line here, you probably can classify things into insulators and metals. If you see that the dots are actually all over the map with no pattern, then that probably means that you can't actually separate out your two classes from the features that you have chosen. Okay, so that's why you always there's no substitute for just plotting the data and visualizing it. Okay. All right. So we are going to split the data. So first of all, we do need to split the data into training and test sets. So here I'm going to choose something different. So instead of doing cross-validation, I'm going to do something much simpler. I'm going to just use the train test split method in scikit-learn model selection package to basically split the data into my training and test set. Okay. Now, something to observe. Okay, so first of all, I create my features. Remember, my features is just 2 features in this case. Okay, it's not like our previous regression problem where we use 9 features for demonstration purpose. Here, our features are there are only 2 features, right? So basically, the mean of the electronegativity and the difference in electronegativity, and the target is simply the class. And here, I'm going to use the train test split to split my x and y into training x, training test y. Training x, test x, training y, and test y. The test set size is 0.1. That just means that 10% of the data will end up in the test set. 10% of the data is going to end up in the test set, and 90% of the data is going to go into the training set. Okay. I'm also setting the random state. This can be any integer you choose. The reason why you do it is just to set a random seed such that every time you run the code, it's going to give you the same result over and over again. Otherwise, the random seed is set based on the time at which you run the code, in which case you will get non-deterministic result every single time you run the code. Okay, so this is just more for testing purposes. Okay. All right. Any questions so far on the code and preparation? No? Okay. So in lab number 2, you will have to go through all these things, but obviously it's not exactly the same problem. You have to figure out how to do that in your lab 2 in terms of data preparation before you actually start training your machine learning models. Okay? All right. Now, let's start with one of the simplest ways in which you can determine, you can use to use a linear model to do a classification task, right? So if there are k classes, in other words, instead of the binary problem where we have just 2 classes, in a binary classification you only have metal, insulator, just 2 classes, right? But hypothetically, let's say you have k classes. Basically, what you can do is that you can have a m by k indicator matrix, response matrix, and each row is basically just a vector. Okay, so you have a row vector which indicates, well, in this case, the first row, the first observation is in the k class, the second observation is in the first class, the last observation is in the second class. Okay, so in other words, if my first row is in the k class, I put a 1 on the k column. If since my second row is in the first class, I'm going to put a 1 in my first column and 0 in all other columns, and so on and so forth. Okay, so every single row is going to be just a single 1 in the column in which you, in the class that data point happens to sit in. Okay, so this is also why it's called a one-hot encoding. Okay, so in other words, you put a 1 in the category in which your target is in, right? Now, what we then do is that we are essentially saying each of these columns is basically a single response variable. And once you have that, you can actually just use your standard linear regression, right? So what you're going to do is that you're going to take the k response, which is this let's say in this case, let's say we choose the first column. And if the first column is one set of observations, we will have one set of beta coefficients for that column given our input features. Okay. Now, what you then do is that after you train your linear regression model, you are going to basically predict the values for every single value in this response matrix. And then, of course, you're not going to get 0 and 1 now. You're going to get some predicted value since it is a regression model. And all you are going to do is that you're going to say the highest value in this in a particular row indicates basically the class in which indicates the predicted class. Okay, so that will basically divide your input into different regions, and you can also, of course, choose your input features in such a way that you can, for example, augment it with polynomial functions, other basis functions, and so on and so forth, right? And all those will then lead to nonlinear decision boundaries. Okay. So once you do that, this is your standard linear regression problem for each column. Your standard linear regression basically has a well-defined analytical solution. Okay, this is basically your least squares regression problem, least squares solution to find y. Okay, and what you're going to do is that you're going to find the largest component, and we will take that as basically the classification k. Now, this is an example of a toy data set. Okay, you can see here that quite clearly there are 3 categories, right? There's one category here, one category here, and one category here. Now, the problem with this kind of simple linear regression approach to try to predict classes is that sometimes your classes can be masked. Okay, what this simply means is that even though there are 3 classes and you actually have 3 decision boundaries, what you end up with is actually only a single decision boundary, and you essentially only get 2 classes. So everything is classified into either group 1 or group 2, and nothing is group 1 or group 3, and nothing is ever classified into group 2. Okay, so this is one of the problems with this kind of linear regression approach to classification. Okay. Now, what is a more sophisticated approach, right? A more sophisticated approach is what is known as discriminant analysis. Okay. Now, discriminant analysis is based on Bayes' rule, right? So, as one of the prereqs for this course, I'm expecting you to know your probability and statistics. You should already be familiar with what Bayes' rule is. Bayes' rule simply states that the probability of G equals to of your observation being in class K given your observed feature set is just equals to the class conditional probability density multiplied by the prior probability of being in class K divided by the sum of your multiplication of your class conditional probability for each class and the prior probability for each class. Okay, so so this is basically a statement. This is basically your Bayes' rule, right? Now, obviously, when we are doing this, one of the biggest thing you have to assume is what is your class conditional probability, right? What is the form of your class conditional probability? There is no guarantee it can be any certain well-defined form, okay? But the most common approach is that we are going to assume the most common distribution that is out there, which is the Gaussian distribution, right? So we are going to assume that the class conditional probability of each class K takes on the form of a Gaussian, right? And this is basically your Gaussian distribution. You can ignore the complicated notation. You can just think of this as basically a vector form of x minus mu squared, okay? There is something called a covariance matrix. This is your equivalent to your 1 over 2 sigma squared, which is your standard deviation, your variance, okay? And this is basically 1 over square root 2 pi square root sigma, okay? Now, so this is just your normalization factor, right? So don't need to, this is the actual vector format of a Gaussian distribution, matrix format of a Gaussian distribution, but you just need to be aware that this is the general form, right? Now, you then need to make some estimate of the prior probability distribution. In other words, if you are not given any information, what is the probability of a data point being in class K, right? And the usual way of doing this is quite simple. You take your data set and you see, well, if out of 10 data points I have 3 which are metals, then my prior probability of something being a metal is 3 over 10, right? It's a very, very simple way of estimating the prior probability, okay? So, so in what is called linear discriminant analysis, another assumption is made, which is that the covariance matrix are all the same. So in other words, no matter which class you are in, you have essentially almost the same standard deviation, okay? That's the way that I'm going to describe it, right? And if you have the same standard deviation, what we can do is that now if you want to decide is something in class K or class L, we can look at the posterior probability of the observation being in class K given the feature vector x, divide by the posterior probability of being in class L given the observation x, and we take the log between them, okay? And if you substitute in this particular formula for your posterior probabilities, you get essentially this expression, and then you substitute in your normal distribution assumption for your f of k x and f of l x, you essentially get this expression over here, right? Now, at the boundary between k and l, in other words, at the boundary where essentially you are indifferent between whether something is in class K or class L, the two posterior probabilities must be equal, right? So if the two posterior probabilities are equal, then that's just log of 1. Then you basically, this term goes to 0. And you are essentially left with this equation, which you can see is linear in your variable x, right? There's only x to the power of 1. There's no x squared, okay? So this is a linear equation in x, and you then have to go ahead and solve all this entire series of equations to compare all the different combinations of classes, okay? So in other words, you have to compare class 1 and class 2, class 2 and class 3, class 1 and class 3, so on and so forth, right? So for all your k classes, right? Now, so since we do not know the prior distributions and covariance matrix, we will estimate it from the data. As I mentioned, the prior probability of being in class K is you just take the total number of data points that you have in class K divided by the total number of data points. The mean of each data point, you just estimate it by taking the observed feature vectors divided by the total number of data points. And for the covariance matrix, you can also estimate it using your standard statistical way of estimating variances, essentially, right? Now, The good thing about something like this, the linear discriminant analysis, is that it avoids the masking problem that you have with standard linear regression classification. Okay, so for our meta-insulator data set, what you will get if you run a linear discriminant analysis is something like this. Okay, now I'm going to go through the data with you, the code with you on how to do linear discriminant analysis. Okay, so now in scikit-learn there is the module called discriminant analysis, and under discriminant analysis there is your linear discriminant analysis. Okay, I have written some code to basically plot that nice plot that you see, basically the color map plot that generates colors based on the classes. Okay, so I'm not going to go through the details of how that color map is done. You can go and read it yourself. Okay. The more important thing is how you go about running a linear discriminant analysis. So this is the relevant line over here. Okay, you essentially initialize your linear discriminant analysis. You need to select the kind of solver for this particular problem because it's so simple. It really doesn't matter which solver you use. Okay, I wanted to store the covariance because I'm actually going to use the covariance matrix to plot the distribution of the data, and then you just feed your linear discriminant analysis model with your training data. So you give it your training X and your categories Y, and then you basically can ask the model to make a prediction given your test set. Okay, and I also wrote a method to basically plot the data for both the linear discriminant analysis model as well as my test X and test Y. And basically what you get is this plot right here. Oh, okay, wait, I need to run everything. Okay, so I annotated the plot with the accuracy. In other words, this linear discriminant analysis has an accuracy of about 78.9% in classifying the test set in terms of whether something is a metal or insulator. Okay, so it gets right the classification about 78% of the time. Okay, so that is actually pretty good for a two-feature model, right? Now, the white line that you see across here, that's basically the decision boundary. So in other words, everything that falls below this boundary is in one class, which is the metals class, and everything that falls above this boundary is the insulator class. Yes?
Are we recommended to kind of modify this code for our homework, or are we supposed to just kind of build our own learning?
No, you're more than welcome to take the code and modify as you see fit for the lab. Mm-hmm. I would say you would do a significant amount of coding yourself. Mm-hmm. Yeah, I mean, it is my model that good coders code, great coders just copy code. So by all means, go and copy the code and modify it until you can use it for your lab. Okay. And to be honest, I mean, most of this code, I also go to scikit-learn, I look at their example, I copy the code, and then I modify it, right? So, I mean, yeah, do what you need to do, okay? So, as far as I'm concerned, yes, for doing your labs, there's no such thing called plagiarism in terms of copying lines of code, okay? As long as you don't copy from each other, okay? Now, so, the other thing that I want to point out is if you look at these two ellipses, these are essentially the mean and covariance, the fitted Gaussian distributions of your feature set. Okay, so the stars are basically the means of your data, and these ellipses are basically the covariance distribution of your represent the covariance of your data. Okay. And you will notice that the two ellipses look exactly the same in this case because, just to reiterate, for linear discriminant analysis, we are making the assumption that all the data have the same, all the classes have exactly the same covariance matrix, okay? So the ellipses will be exactly the same, okay? Now, of course, this is not a perfect segregation. You will see that there are data points that are wrongly classified. So for example, these two blue data points, they are obviously not supposed to be in this region, but they get classified into this region anyway, okay? All right. Any questions regarding linear discriminant analysis? Yeah?
Is SVD the only solver we have to use for that?
No, there are multiple different kinds of solver. You can play around with them. Sometimes some solvers actually go a bit faster. Some will converge, some might not. But by and large, I mean, for the data sets that we are working with, probably the solver doesn't make that much of a difference. Okay? Okay, now, if you want to move a step up from linear discriminant analysis, there's also something called quadratic discriminant analysis, okay? Now, the only difference between quadratic discriminant analysis and linear discriminant analysis is the assumption of the covariance, okay? In linear discriminant analysis, we are assuming that the covariances of every single class is exactly the same. In quadratic discriminant analysis, we do not make that assumption. We assume that every single class has its own covariance matrix. Okay. Now, because of this this change in assumption, there is no cancellation of terms. Okay. And what happens is that your decision boundaries are no longer linear. Okay. So also, instead of estimating one covariance matrix using your entire data set, you now basically have to take every single class and you estimate a covariance matrix for every single class. Okay? So you can imagine, in this case, I am estimating the covariance matrix by summing across all the different classes this squared, or this essentially squared difference between the data, the observed data and the mean, and I'm calculating it for every single class. In your in quadratic discriminant analysis, you're going to take each of the class in turn, and you're basically only going to do it for each class, and you have a covariance matrix for every single class. Okay, so that's the difference between linear and quadratic discriminant analysis. Now, if you do that, you will see you will get basically a result like this. The boundary it looks like this. It looks like a quadratic function. Okay. Now, the other thing that you need to observe is that basically now my ellipses are no longer the same, right? It's quite clear that, for example, in my metals class, the covariance matrix has essentially a smaller covariance, right? While for the insulator data set, I have a larger magnitude of the covariance, okay? You also see that the accuracy in this case actually is slightly lower, right? So in this case, the accuracy of my QDA is just 77.8%, while the one for my linear discriminant analysis is 78.9%, right? So it doesn't matter. It doesn't mean that every single time you just make a more complex model, it always performs better. Okay. Now, the application of the quadratic discriminant analysis is actually almost exactly the same. In the discriminant analysis package, there's something called quadratic discriminant analysis. You just, again, fit it with your training data, and then you do your prediction on your test data, and that's basically it. Okay? So if you go back to this is my quadratic discriminant analysis. This is exactly the same set of code that you see for linear discriminant analysis, except that you now have quadratic discriminant analysis over here. And that basically shows you the result, okay? Okay, now another way of doing classification is using what is called a logistic regression model. Now, so the name of this model is a bit of a misnomer. Logistic regression sounds like you are doing a regression problem, but it's actually not. Logistic regression is meant for classification, okay? So the way that logistic regression works is that you are going to model the posterior probabilities from your base rule using a linear function. So I'm going to take the ratio between my posterior probability of being in class 1 divided by the posterior probability of with that of being in class K and the log, and that log of that function of that ratio, I'm going to assume that it can be described by a linear function in my features. Okay, so beta 1 naught plus beta 1 transpose x, and so the betas are essentially the coefficients of the linear function that I have to solve, right? Now, if you have k different categories, you basically have k times k minus 1 divided by 2 combinations, and essentially you have all these functions that you need to solve. Okay. Now, if you actually go through the math, you will see that the posterior probabilities have this solution. Essentially, you basically have the exponent of the beta 1 naught plus beta 1 transpose x divided by 1 plus this the sum of all the exponents for your being for the posterior probability of being in class 1, and for the posterior probability of being in class K, you just basically have 1 over this same denominator. Okay. Now, for those of you who have done thermodynamics before, this reminds you of what? Exponent of something divided by the sum of the exponents or something. Statistical mechanics, anyone? This looks like your partition function. Okay, so your partition function is e to the power of negative beta e divided by the sum of e to the power of negative beta e. Okay, so it essentially is roughly the same form. Okay, all right. So to actually find the coefficients beta, you usually solve it using what is called a maximum likelihood approach. In other words, you define the likelihood of beta as basically equals to the sum of the posterior probabilities given your beta, and essentially you just differentiate that loss function with respect to beta, you set them to 0, and essentially what you get are equations that are nonlinear in beta, and you are going to solve that equation, those set of equations using some optimization algorithm. Okay, so either Newton-Raphson or one of your other optimization algorithms. Okay, and those details I'm not going to go through, but I'm going to show you how you go about doing it in scikit-learn. Interestingly enough, in scikit-learn, your logistic regression model is in the linear model package. Okay, so you just initialize your logistic regression class. Here for the solver, I choose the LBFGS, which typically is a good one to use. Other than that, the API is exactly the same. You still feed it to your training data, you predict on your test data, and then you then I make a plot, okay, of the classification, and essentially this is what I get. In this case at least, the logistic regression gives you almost exactly the same result as your linear discriminant analysis. The accuracies are similar. You still get a decision boundary that looks like a simple straight line. Okay? All right. Now, as a final topic for classification problems, I want to talk a little bit about what are some of the loss functions you would use for a classification problem. Okay? Now, remember, in regression, there are two very commonly used loss functions. One is the sum of squares, okay, the sum square error. The second one is the mean absolute error, right? So those are your two common loss functions for your regression problem. A classification problem, you should not be using those two as your loss functions, okay? Because let's consider a very simple example, right? We only have a binary classification with two levels, right? It's either -1 or 1, right? And the decision boundary about whether to put it in class 1, first the -1 class or the 1 class, is essentially at 0, right? If my prediction of the value is less than 0, I will consider it as in the negative class. If it is above 0, I consider it in the positive class, right? Now, you cannot use something like the square error, because when you make a prediction that has a very, very large positive value and the actual value is in the correct class, you actually don't care about the magnitude of the prediction, right? So it doesn't matter that my model is predicting that the actual value is 1000 when the class is in the positive class. So in other words, if I make the correct prediction that it is in the positive class, I really don't care whether it's predicting +1, +2, +1000, okay? Similarly, if it is making a prediction that it is in the negative class, I also don't care whether it is predicting -0.1 or -100, okay? So if you use the square error, that actually is going to make a difference, right? Because if I make a prediction of 100 versus 1, the square error is basically 99 squared, right? So so we are penalizing that correct prediction, okay? So we shouldn't be penalizing a correct prediction. So in loss functions for binary classification, we need to define a loss function that is positive when the prediction and actual value is in the same class, and negative when they are in opposite classes. And they have to behave in a non-symmetric way. So in other words, when I'm making a wrong prediction, the bigger the value of the wrong prediction, I would want to penalize it. But when I make the correct prediction, I want to make it such that I don't actually have any, the penalty doesn't increase as my correct prediction increase in magnitude, right? So we can define something called the margin, which is basically your actual observation y multiplied by the predicted value of y, which is f of x. So if I take the multiplication between them, you can see that when the prediction and actual value is in the same direction, so in other words, if it is +1 and I predict +1, it is a positive value. If I make a wrong prediction, this margin is going to be a negative value, right? Okay, so how do I actually go about constructing a loss function that works? So I can take the exponent of the negative of the margin, okay? So you look at this function, how does it behave, right? When the value is extremely positive, which means that if I make the correct prediction, even if this value is very, very much larger than my actual observation, e to the power of negative very large positive value is going to go to 0, right? So in other words, there is very little penalty or loss associated with a correct prediction. Now, when I actually make a wrong prediction, in other words, if my y and f of x is different signs, then this becomes a positive number, and the exponent of a positive number is a very, very large positive number, right? So, so this is why it's called an exponential loss, okay? So for classification problems, this is a very common loss function that you use, okay? You are penalizing the wrong classification, and you are making very little penalty on the correct classification, okay? There are also other loss functions that you can use when you don't have just a simple binary classification problem. So for example, if you have k classes, you can define what is called the binomial or multinomial loss, okay? So in this case, this takes on this expression that you see right here, where you essentially define the loss with respect to classification in different categories, okay? So just to show you, like for binary classification, what are some of the loss functions that you can use? There's the exponential loss that I just talked about. That's basically the blue line over here. You can also define something called the binomial deviance, that basically is this line over here. I want to show you basically if you use just your squared error, you basically have this red line over here. So in other words, you have low losses only when you get the value exactly equals to 1. You get very high losses when your values are when you have a wrong classification, but you also have very high losses when you make the correct categorical prediction, but you actually make a wrong value prediction. Okay, so this is why you don't use squared error for binary classification. Okay. All right, that's the end for linear classification. So